Hi, folks. Welcome to another exciting episode of YouTube Live, YouTube Monday Live. And we are going to be talking today about dark comets. Perfect for this spooky season that is upon us. Halloween is just around the corner. And all of you, I hope you all know that Halloween is an astronomical holiday. It is a cross calendar date that falls between the solstice and the equinox. There are four of those. Other ones are May Day and oh heck, Groundhog Day is one, and I'm blanking on the fourth. Anyway, so it's the season, it's that time of year, and we are going to be talking today with Aster Taylor. Hi Aster, how are you
Hello,
doing?
I'm
It's good
doing
to
well.
see
How
you.
about you?
So Aster here is the discoverer of dark comets, or among the group who discovered
There we go.
the, the dark comets, and they are a graduate student, a Fannie and John Hertz Foundation fellow and graduate student at the University of Michigan. And I'm going to just have to dip out of this picture for a second. They received their undergraduate degree in astrophysics at the University of Chicago in 23. Research interests include planetary formation. Oh my goodness, I cut off part of my notes. Celestial mechanics, fluid dynamics, exoplanets, and solar system small bodies. And that's what we're going to talk about today, isn't it, Aster?
Yes, it is.
Okay, so dark comets are sort of a hybrid, or are they? Tell us the different. First, tell us what is a comet and what is an asteroid. What are those?
Absolutely. So this is a very historical distinction. When we looked out into the night sky and we saw objects moving on the sky that we later learned were in the solar system, we categorized them as either asteroids or comets, depending on if they were small point sources, if you looked at it and you could just see a dot in the sky, or if there was a
Oh,
fuzzy cloud around it called a coma, which is
coma.
why it's called a
Okay,
comet.
right.
Versus an asteroid because it's an aster. It's a star-like object. It's a small star.
Ah,
So
okay.
stars also look like point sources. So this is the classic distinction that we have between asteroids and comets. We later learned through a lot more investigation that there's also somewhat of a physical distinction. Asteroids are very rocky bodies that are generally in the inner solar system, and
Okay.
comets are very icy bodies that are in the outer solar system. That's the
Okay.
general division.
So,
There's a mix up
so
there.
that's the classic dirty snowball description, then, right?
Exactly. That's the classic idea.
Okay.
Recent work has shown that this is not a true binary. There's plenty of stuff in that sort of interim space. And one of the objects that we're talking about today is the dark comets. Dark comets are objects in the near Earth environment. So they're close to the Earth, where we would expect asteroids to be. And they
Okay.
look like asteroids in that they look like points if you look at them on the sky, but they have some sort of non-gravitational acceleration that has to be explained. We're very confident that it's going to be explained by outgassing, which
Okay.
is
So
volatile
when you
on the surface. Sorry.
I'm sorry, I didn't mean to cut you off there.
Please do.
When you say non-gravitational, what you're saying is that something in the interior of these dark comets is melting when they get warm enough and creating a jet that propels them. Is that what you're saying?
Yes, that's our idea. We know this because you can track the positions on the sky, and you know how gravity works in the solar system very, very well. So you say, well, in 10 years, this should be here, and it's actually here. So there's
Oh,
something happening to it that's not from gravity. And you can calculate that. And there's other effects, non-gravitational effects that work on asteroids. But this is too large for any of those.
like what?
Radiation pressure and the Yarkovsky effect. Generally, the asteroid will absorb sunlight, and that sunlight will give it some momentum, and that
But
acts as an acceleration. And
it's
it's
uneven sunlight, so one side is pushed more than another. Is
exactly
that
one
right?
side's pushed more than the other. And this is not gravity, but it's a
No.
sun effect. And that's obviously a very small effect, right? They're
Right.
relatively large objects. Sunlight's not super strong. You don't feel pushed on it
No.
when you're on the ground. So the fact that it's moving larger than that implies that there's something else going on. What we
Something
expect.
else. And so that's what makes these objects unique, is that
Mhm.
they look like an asteroid, but they move like a comet. Is that
Basically,
kind
yeah.
of it?
Basically, yes. And they're
Okay.
called dark comets because they don't have any coma. We can't, or at least
Interesting.
we can't observe the coma. It's
Okay,
too
so
dark for us to see it at all.
this, when we say dark, when we say a dark
Mhm.
comet, we're not talking about dark as in dark energy or dark matter.
Absolutely not.
Some things that can't. So these are readily detectable, right?
Relatively, yes. Like it's
Relative.
not as readily detectable as any near-Earth object is, which is varying degrees of difficulty depending on position and all this sort of thing. They're
Sure.
not invisible. The reason that
Not
we call them
invisible.
dark
Okay.
is that we expect them to have a coma, some sort of fuzziness around them from the outgassing, from the ices melting, and they
Right.
don't. It's too
So if
green.
you've been looking at A3 in the night sky recently, you can see that that's not a point source. It's not like a planet or a
Exactly.
star. Well, a planet is not technically a point source either,
It's
which
close
is
enough.
why they don't shimmer. But the distinction is clear when you're looking at a comet with just your eyes. You can see that it's not a star. It's clearly spread
Yeah,
out a little bit,
there's some
and that's
fuzziness
not the
around it and a little bit of a tail.
right.
We
But
can't see
that's
them.
not the case with these.
We can't see them.
No. Okay. But they're still moving like so. I think we've set the stage here of what exactly a dark
Mhm.
comet is versus a regular comet versus an
Yes.
asteroid, and there seems to be a spectrum. Is that what you're saying? Sort of a spectrum of
Yeah,
these
there's some
bodies?
sort of continuum. We expect there to be if you imagine, this is not really meaningful, but if you imagine some sort of two bimodal distribution where there's a bunch of very rocky objects and some very
Uh-huh.
icy objects, you
Okay,
expect there to be that distribution, but then you also expect there to be stuff in the middle that sort of
right.
mixes and matches the categories. And so the dark comets fall in there. There's a bunch of other objects like main belt comets and Manx comets and all these sorts of things that sort of have different mixed and matched properties of asteroids versus comets that sort of fall in that middle space. And dark comets is one of them.
Okay. So one thing that we know about comets is that they generally come from the outer portion of the solar
Mhm.
system, perhaps the Kuiper belt, or
Mhm.
these aren't coming from there, are they?
I
These
don't
are
believe
local
so.
things.
They're in the near Earth environment, so they're all orbiting relatively close to the Earth. And by relatively close, I mean anywhere from uh, anywhere from an AU to 3 AU on a variety of orbits that are either close to the Earth or out to Jupiter, back into the Earth and back out. But they're all between Jupiter and the Earth, roughly.
They're all between Jupiter and the Earth, and is that a coincidence or is there something
Uh,
going on
it's
there?
not really a coincidence. That's mostly an observational effect. It's really hard to
Oh,
find stuff closer to the sun than the Earth because you have to look at the
okay,
sun.
right.
And it's all the stuff that's sort of close to the Earth because then it's much easier to find stuff if it's close to the Earth. So
Makes sense.
these are observational effects. But one of
Okay.
the things, hmm. but so
Well,
the distinction that we have is they're not from the outer solar system. They're not on these very long period orbits that go out past Jupiter. They're all in this sort
right.
of close-in environment. And we have some ideas about where they're from, but we don't have anything definitive yet.
Well, where do you think they're from then?
We
Let's
think
talk
that they
about
are
the
from
idea.
the main asteroid belt. If you do dynamical histories, if you run a ton of simulations of objects in the asteroid belt, the
Mhm.
ones that the primary source of objects on these orbits is the inner edge of the asteroid belt, where interactions with Jupiter and Saturn will knock objects out of their orbits and send them
Oh,
flying inwards.
yeah.
That's
Send them
also a
flying.
major source of all near-Earth objects. So
Right,
almost
right.
anything in the near-Earth environment is going to come from that source or from another source of stuff in the asteroid belt. But we think that these are the ones pushing these objects inwards. And what's weird
Okay.
about that is that the inner asteroid belt shouldn't have a lot of ices on it.
No.
So the fact that we have these objects that apparently have some sort of volatile composition that are from the inner main belt gives us an interesting new insight into what could be in the inner main belt.
So we could be discovering really some foundational things about early solar system objects, how
Yeah,
things formed, right?
yeah. So
Now,
this is the whole story that we have.
this is the whole story that we
Mhm.
have. Okay. So you mentioned they are near Earth objects, but you described 1 to 3 astronomical units. And the astronomical unit, for anybody who might not know, is the average distance between the Earth and the Sun. So these are not getting real close to us, are they? Not
They're
generally.
getting not real close. So when I say they're 1 to 3 astronomical units, that's not the distance between the Earth and the object. That's the
No,
distance between the object and the sun.
I
So
see.
what we consider is when we say near Earth object, there are very few objects that are just sort of sitting, hanging out near the Earth. These are
Right.
objects that are orbiting on orbits similar to the Earth's, but offset by a little bit. So
Oh,
they'll start here. This is the Earth. This is the object. The object will come down and around. The Earth will go around, and they'll come back to about the same point. So they'll sort
okay.
of come in and out next to the Earth, but they're all sort of in the environment around the Earth, moving around.
So
So
these are Earth crossing
Earth
objects.
crossing or just outside of Earth crossing, but getting close. The
So
whole
that
thing
means,
is the near Earth environment is anything that gets relatively close to the Earth at some point in its orbit.
right. So that means these possibly could and probably have collided with our home planet then. Is
Yeah,
that,
so not these objects, but in particular, these
well,
objects
not
we've done
these?
they certainly haven't yet, and we've done long-term
No.
simulations, and they won't within the next 100 years,
Oh, well, that's great news
which is
because
great news.
yeah, for
Um,
us.
yeah, it's great news for us, but they certainly could have in the past. It depends on how many of them there are in the near Earth environment. We know that near Earth objects have collided with Earth in the past and do so on a somewhat regular
Absolutely.
basis. If there's only 7 of these in existence, then it's unlikely. But there's certainly more than that. You just don't know how many. But it's likely that some have collided with the Earth in the past at some point.
Okay. When you say 7, that's the number that you've positively identified
Yes,
thus
that's the
far,
number
is that
that
what
we
we're
know
saying?
of right
Okay.
now.
All right. Um, so there is a mystery, and that mystery is, how did Earth become a water planet? Where did this water come from? Is your research leading us to maybe think these could be a source of at least some of that water?
Yeah, so there's the like you said, the mystery is we don't really know where Earth got its water from. It certainly didn't form with the Earth. The Earth was at one point made and there wasn't water on it, and then it got water delivered. We don't quite know where that water was delivered from. We know it wasn't from comets from the outer solar system. It
Hmm.
might be from comets in the outer main belt.
Okay.
Um, the thing you look at is isotope ratios of how much deuterium and hydrogen there is, which traces where in the solar system this thing had to
Oh,
solidify. And
that's extremely clever.
it's very, very clever. And the ratios do not work at all with outer solar system objects, and they look like they work for inner solar system objects, but we don't really have a ton of idea. When I say inner solar system, I mean outer main belt. So we haven't measured those isotope ratios on these objects. If we did, we could either say maybe or definitely not. We haven't made those
Right.
measurements because we don't have any detections of this torque that would allow us to do that. But it's certainly quite possible that if there is a relatively large population of these icy objects in the inner main belt that are regularly entering the near Earth environment, that these objects could hit the Earth and be responsible for delivering at least some of the water. We don't know the actual fraction. That requires a lot more research. But this is a new pathway for delivering volatiles into the near Earth environment, which could be responsible for actually getting the water onto the Earth's surface.
So this could be one of the mechanisms that delivered the universal solvent. Without
Yeah,
water, there is no life. None of the biological processes can
absolutely.
go on.
And it's
So
a
this is
possible mechanism. I can't say anything definitive, but it's a possible mechanism, and I haven't ruled it out.
it hasn't been ruled out.
It hasn't
Well,
been
it
ruled out.
certainly seems plausible, but that's why we do science, is to make sure that the plausible is the actual.
Exactly.
Speaking of doing the science,
Mhm.
um, I'm gonna give it a shot here. Now, Hayabuza II, I
Yes.
assume, is the name of the probe that's already on its way out to visit an asteroid, and it just so happens to be one of the 7 that
Yep.
you and the team that you're with, have identified as a dark comet. So that's got to be pretty exciting
It's very exciting. We're
and lucky.
by sheer coincidence. The
Wow.
object that they didn't know it was a dark comet when they chose that target. So somewhat by sheer coincidence, we found these objects with non-gravitational accelerations and said, "Oh, look, we're sending a probe to one of them already," which is going to be very, very helpful. It'll get there in 2031, by which point I'll be done with my PhD for several years at that point. So it's going to be in a while, but when it gets there, we should hopefully be able to have some additional observations at the surface. We could possibly see if there's any dust or gas coming off of it, which would allow us to confirm that it is in fact outgassing, and we could look at depending on what instruments they're choosing to use and how they're doing their science designations, we may be able to get a better understanding of how these objects got their water, how they're coming out. If it is water, maybe it's something else. Maybe could be CO, could be CO2, could be a whole bunch of different things. It's probably water
Could
though.
be. Could be a lot of different things.
Could be a load of different things. There's a lot of different volatile materials in the solar system. H2 water is the best one, is the most likely one in the inner solar system. And it's the one that we expect to be the primary source of the volatile outgassing, but CO and CO2 are also possible.
So it could be any number of substances frozen into the heart of these
Mhm.
asteroids somewhere, close enough to the surface that when they warm up, how come they how come they're still going after all this time? The solar system is several billion years old, or at
Yeah,
least 4.5.
yeah.
So what's
So
going on there?
they cannot have been going this whole time. There is
No.
simply not enough mass in these objects. If they were going at this rate for the last 4 billion years, it's all gone. If they're going at this rate for the last 100,000 years, a million years, which is how long we expect these objects to live in the inner solar system, in the
Ah,
near Earth environment, they're also all gone. So there has to be something that's turning them on relatively recently. Either they're sort of turning on and off somewhat at random, or they're being turned on, and that somewhat makes sense. If there's like pockets of ice in the interior, as it heats up,
oh,
parts of it will melt, and then that bit will go off and it'll get pushed a bunch, and then it'll slow down as there's no more ice getting melted, and then it
right.
repeats this process. It could also be that one of the things that we suggested was these objects are very small and they're spinning very quickly, the ones that we know about. And so one of the ideas that we came up with was that you could take a much larger object and break it
Uh-huh.
into pieces and have those broken pieces be, and if you do that, those broken pieces are expected to be spinning more rapidly. And
Makes
so
sense.
what we could explain is what you have a main belt object get knocked into a near Earth object, get knocked in. It's
Mhm.
perfectly stable without any outgassing as it spins around. And then it gets broken apart either through getting spun up by other effects or getting
Ah,
struck or something. And when it fragments, suddenly that ice is brought close to the surface and actually begins to outgas. And then it sort of goes quickly and dies out.
okay. So that would explain how they maintain that whatever the volatile is, probably water, in their interior for such a long time.
Mhm.
And it gives you a mechanism for why it's happening now and not in the distant past.
Exactly.
Yeah,
And we
that's
know it has to
cool.
be in the interior. The one of the
It
things
has
with
to
the
be.
inner main belt is that the surface of objects in the inner main belt is hotter than the sublimation temperature of water. So
Yeah,
all these asteroids that are in the inner main belt, they can't have surface water because
because we're in the Goldilocks zone,
it would
right?
evaporate away immediately.
It would be
So it
gone.
has so these objects have been sitting there for 4 billion years. They've lost all their surface water. But in the interior, you can store some ice. So you have to get that out somehow. You can either make it much hotter on the surface, which you get
Mhm.
when you get closer, and that can boil off some of it, or you can break the whole thing apart and then it just becomes surface and then it vaporizes immediately.
That makes a whole
We
lot
don't
of
have a
sense.
strong idea, but it makes sense. And the theory works out. We haven't made enough observations to be able to know if that's true or false, but that's the idea.
But we'll have come 2031, we're going to have a whole lot more
Absolutely.
immediate data. Do you think we're going to be able to detect? We'll be able to detect the coma itself when we get close enough. It is not extremely visible, and why is that? Why is the coma of a comet so obvious while these are clearly not obvious?
So we should be able to detect it as we get closer, and there are some instruments on Earth that we think we might be able to detect it with.
Oh,
So if we pointed James Webb at it, JWST at it, we
mhm.
think we can probably get a coma. Hopefully, we've
Hopefully.
applied to James Webb to let us do that, and we'll see if they say yes.
It
Um, it's always a difficulty, but
is.
the basic idea is that the outgassing is large enough you can detect it by the motion of
Mhm.
the object, but it's small enough that you don't necessarily expect to see the coma. It's just such a small, the objects are so small that even a small amount of stuff coming off of it will make it move in a way that's significant. But it's not enough that you can actually observe it using a telescope. Another possibility is one of the things we have to look at is we don't actually observe any of the gas coming out of these objects. For most comets, it's very hard to observe the gas because it's
Oh,
just so thin and
right.
the wavelength is such that it's really hard to actually observe gas. What you can observe is dust. You can observe the dust that's being pulled out by the gas as it goes. So if you look at
Okay.
a comet, the tail sort of comes off and to the side, and that's because
Mhm.
that's dust being pushed out that is then drifting behind it as it orbits. If you look at it in different wavelengths and very carefully, you can sometimes see a second tail that comes straight out behind it. And that's the gas that's being pushed out by the sun.
Ah,
So you'll
okay.
see these two different tails. And so we have to look at the dust in this regime. And the dust is just not, there's just not a lot of dust. So you're not expected to see the coma. It's also possible that it's only sometimes active, that like I was telling you about. And
Yeah, that would.
we've only observed it a few times. We haven't made deep observations of it over its entire orbital period. And we've seen this motion over the course of 10 years. So it's quite possible that it's just gone off a bunch when we don't see it. And then that comes back around and we say, oh, look, it's in a different position. It must have had some sort of motion in that past 10 years, but we've only observed it these few every 5 years, and it went off when we were looking at it. So we don't really know. People are doing some observations of these objects when they're very close to the sun, when we expect them to be the most active. And we're hoping that JWST gives us some time to actually take a look at the surfaces and try to piece out surface features and try to find the coma itself.
That would be spectacular. I can't wait to see those images. Now, you have identified 7 of these things, but there are many, many asteroids out there.
Mm-hmm.
How many might there be? How many dark comets moving non-gravitationally under their own outgassing could be out there? A
lot. It's very hard to know. We have done our best in this paper that we're talking about today to measure it, and it's somewhere between 0.5% and 60% of near-Earth objects are explainable. That's a massive range. Could be 60, could be a half. We don't really know. We just don't have, because we're trying to identify these with non-gravitational accelerations, we need to have very long time scale orbits. We need to be able to have seen these objects for 10, 12 years to be able to find the small changes that we're looking for. And most of the near-Earth objects have not been observed for that long. And so it's just hard for us to say, a significant fraction of the objects could have non-gravitational accelerations this large. And a significant fraction of them could very easily not have that. It's just very hard for us to know because we can't observe it. One image isn't enough. You need such a long baseline that there are very few objects that have had that length of time.
Right. So perhaps this isn't the interest of your research team, but do you think other researchers might be going back to mine old data to see if we can't get more of a handle on how many of the asteroids in the local area around Earth are actually moving of their own accord without gravitational?
For sure. There's a group that I'm a part of. I'm part of the group, the team that originally discovered these. And so the authors of that paper that first identified these objects are doing more looking back through archived data to try to find more of these motions. And they're working on, they've finished their investigation and they're working on getting out the results very soon. I can't talk about the results because they're still under embargo, but people are looking into this and they're hopefully going to shrink the space. The other thing is that because what we really need is much more high precision observations of positions of all these objects, that's going to take time and that's going to take more surveys. So when the legacy survey of space and time on the Vera Rubin Observatory goes online, we should get a lot more objects and we should get a lot more observations of old objects. That should help us to lengthen the baselines and increase the precision of these observations so that we can hopefully start to pare down that large range.
That enormous range from half a percentage to almost 2/3.
Unfortunately, that's the statistics. We have trouble with this sort of thing. Not a lot of data.
Well, it seems to me that this makes, from what I know of planetary formation, solar system formation, that this makes perfect sense that some of these volatile gases would have been confined egg-like inside rocky bodies. And when they break up, obviously, suddenly the volatiles are exposed to the warmer environment and begin to outgas and push them around like comets. Absolutely. So it turns out that maybe cometary motion is not relegated just to comets, maybe a lot of objects.
Or it's possible. There's more than that.
It's possible.
Now, we certainly expect that there are going to be a lot of objects, especially in the inner main belt, that don't have any volatiles, because anything that sort of formed there in the early solar system isn't going to gather any ice around it. The ice is not going to be solid. It's going to be a gas out in space. And so it's not going to be contracting down onto these asteroids. What we're going to run into, though, is in the early solar system, the outer giant planets moved around a bit, and that mixed up all the objects in the asteroid belt. So we took a bunch of stuff that was formed farther out and had ices, and formed farther in and had no ices, and it mixed them together. And it's hard to know how many it mixed, right? It could have done it 50-50. It could have done, it's a very messy, chaotic environment that's very hard to pin down precisely. And so the fraction of objects in the inner main belt that actually have ices tells us about the motion of the planets in the early solar system.
So maybe you could sort out your population using the same technique that you described earlier of isotope identification. That might be.
It's quite possible. It's very hard to do isotope identification because you need to really get very good observations of the outgassing, because what you're really looking for is very small differences in spectral lines, which is just very hard to get. So you need to see something coming out. We can't do that for these objects because they're too dim and they don't have a detectable coma. If we could actually get the gas coma with a good spectrograph and make high precision observations, we may be able to separate those out. We don't have any plans to do that because it's just too hard, even with JWST.
That sounds like it's in the far future, if it ever happens at all. Something to look forward to, something to
Maybe
guide your career.
We'll see. I think that has a spectrograph. It actually does.
Okay, so what does this tell us? Let's step back just a little bit here. What does this tell us about the solar system formation in general? Does this give us any more parts to the story, to the narrative of how we came to be here, floating around?
So it's another piece of the puzzle, right? We need a lot more research to figure out how that piece fits in. But the existence of these objects tells us that it may be a part of the story of how we got water to Earth. And the existence of a volatile reservoir in the inner main belt tells us is another piece of the puzzle about how the solar system formed and evolved. There's an old way we talk about this, which is that, the solar system is, the way that we talk about solar system history is we're telling a story. We have all this evidence. We try to tell a story that fits the evidence, but we just have so much evidence. It's really hard to do this. And it's so complicated. You could tell tons of different stories that match this evidence relatively well. So the thing that we could do with this is this gives us another point. We could try to nail down exactly what fraction of the inner main belt has volatile material. And if we can get that nailed down, that gives you another constraint. And the story has to say, well, you have to do the mixing, and you have to get about this much mixed over. You can't have it be none. You can have it be 100%. You can sort of nail it down a little bit. And then,
so that's going to tell. Oh, please continue. Don't let me
stop. The other bit of, this could get water to Earth. And so having that be available gives you an additional story that you can tell, and an additional way to say, water comes in from the main belt, comes in from the outer main belt, comes in from wherever you like, as long as it matches the data. It gives you another path to get water to Earth. We can't fit that together quite yet, but hopefully we can in the future with more observations and better measurements of isotope ratios, etc.
Well, now that you've made a real hit with a dark comet, what's next on your agenda personally? Where are you going from here?
I have a bunch of work that I'm doing. We've just submitted a JWST proposal to actually make observations of these objects, of two of the objects, and hopefully to try to pull out some spectrographic surface features to figure out if there's ices on the surface, how much there are, what is the surface made of, what's its sort of details like that. Not actually not physically resolving it. So you can't see, here's a rock, there's a rock. But looking at spectra and saying, well, clearly about half of it has some water because here's a bunch of spikes from water, etc. We're submitting an observation plan to do that. Hopefully we get that approved. In the meantime, I've written a paper about looking at whether or not there's a sampling bias against non-gravitational accelerations in the way that we detect these objects. Because the way that this operates is, you have an observation, and then you wait 10 years and you see another observation, and you link it back up using the orbits to say, oh, we have this chain of observations here and this chain here 10 years later. And the orbit through this one goes all the way around and matches up here. So this is the same object. But if it's moving from where you would expect it to be because of gravity, you may say, it's a different object. It's a new object that we haven't observed before, when it actually isn't. So I'm working on a project to actually look into that and to see how important is that effect? Are we going to miss objects with non-gravitational accelerations because they're moving on the sky more than we would expect? And then there's also tons of other projects about planet formation and solar system formation and stuff like that. I have a lot going on.
Many things on your solar system plate.
Interesting.
Well, Aster, thank you so much for joining us today. That was
Absolutely.
a remarkable explanation. This is fascinating. I'm really, really thankful that you could join us and explain
Thank
this.
you very much for having me.
Yeah, you're welcome. Folks, we've been talking to Aster Taylor, who is a postgraduate student at the University of Michigan and one of the co-discoverers of dark comets that you just heard about. Thank you for joining us.
Thank you
But
very
come
much.
on back, because on Friday, this Friday, November 1st, we are going to be sitting, that is we, not we, but Debbie Bird will be here with Sean Dahl, he is a space weather forecaster for NOAA, and we're going to be talking, or they will be, solar cycle 25. So that'll be really interesting, and that is going to be at 12:15 on Friday. That's 12:15 Central Time, which is 17:15 Universal Time. And then on November 11, we are going to be talking about where is everyone, figuring out the Fermi paradox with Alan Stern, and that will be on the 11th at the same time, same bat channel. Again, Aster, thank you very much for joining us. Really appreciate it, folks. Like, subscribe, visit EarthSky, share this around. You probably know somebody who would love to hear about this stuff. Remember, it's one Earth and it's one sky, EarthSky. Thanks again, folks. We'll see you next time.
All right.
All right, we're clear.
Sounds good.
That was great, Aster. That was absolutely fantastic.
Thank you. I'm glad you enjoyed it.
You did well. You did really well. You did really well, and we are fully uploaded. So that's it.
Beautiful.